Factors for material fatigue testing. We're going to start by looking at an overview of what an EN fatigue test looks like, and today's focus is going to be looking primarily at strain life material testing. We'll then go in and we'll start to look at what's required to specify a fatigue test. Walking away, you won't be able to do a test, but hopefully you'll understand the key requirements. If you've asked to have a fatigue test done, the answers to questions that would be given to you. And so we'll talk about various test specimens, the overall test setup, look at some of the test results that will come out, and then we'll have a summary of what I consider to be the important factors driving this. When we do fatigue, we have a variety of different damage models we can use. We're going to focus on strain life or crack initiation. And in order to do that style of analysis, we need to have a strain life curve. The strain life curve is actually developed with a series of constant amplitude strain tests. We use strain life because it actually looks at total strain, elastic and plastic. Tracking the plasticity actually mimics what governs fatigue, and hence gives us an ability to do both low cycle and high cycle fatigue. It also gives us, because of plasticity, the ability to track residual stresses that occur due to loading. What we're going to end up with is a curve, as we see down in the lower box, that is basically plotted on a log-log scale of total strain, amplitude, and life. And that curve, represented by this equation, basically is going to be what we use for a fatigue calculation, looking at a combined low cycle, high cycle fatigue. Those individual test data dots you saw on the curve are basically tests we run on a specimen. And the concept of this specimen, we want to generate specimens that represent as closely as possible our part. Hence, we want the specimens to actually be made of the same composition material, have the same microstructure, the same heat treat, manufacturing processes as our part. Now, with that may actually control the overall size of the specimen. As you see in the upper picture, we have the ability to pull specimens out of our parts, but doing that is actually driving the size of the specimen. I've only got a certain amount of material area that I can actually utilize. The overall shapes of the specimens are driven, one, by the part geometry. And so we'll see that there are typical specimens that are cylindrical that would be used for things like wrought or cast components. There's also flat sheet specimens that basically you'd use for things like roll stock. That's going to be pretty much driven by the material that you're working with. And the specimens all tend to have standardized shapes. If you go to a particular lab, they'll have a set of specimen shapes for both cylindrical and sheet specimens that they would use. And what you see on underneath the picture of the component is a schematic of a cylindrical specimen. And below that's actually a table of cylindrical specimen sizes that we actually use in our lab in the UK. A couple things to note here. The ends of the specimens are where the grips are going to go on. The key area is actually the center of the specimen, and this designation A is showing you the gauge length. That's the actual area we're going to be measuring the strain at. Now, in terms of specimen shapes, they're pretty much standardized, but the sizes can vary. And again, the size may be completely driven by the material that you're going to actually pull the specimens from. However, if you have a choice, a larger specimen size is desirable. One, as we go to larger specimens, the gauge area, the gauge length, is actually further removed from some of the geometry, those transition areas, hence we can get a more uniform strain field. And secondly, even though the specimens may all look identical, at the microstructural level, they are not. And as we have larger specimens, we can start to reduce the influence that the grain orientation has at the microstructural level and reduce some of the scatter. With the specimens, we now have to basically create these specimens from the material that we're going to be analyzing. And here is actually one of the key aspects to get good fatigue results. The specimens, one, have to be dimensionally accurate. We're going to want to generate a uniform strain field in that gauge length. And we're going to put it, in the test we're using, we're going to put it under tension. We want these specimens to have concentric areas, both at the gauge length where we're measuring as well as at the grips. So when we apply our tension, we're not introducing other aspects like bending. We also want the specimens to be consistent from one to the other. We're going to be looking at trying to characterize scatter in the material, and we want to minimize any sort of scatter across specimens because of dimensional changes. So we want to get those specimens manufactured, but how we manufacture them is also crucial. We want to create those specimens so we don't introduce any sort of plasticity residual stresses in the specimen from the manufacturing process. So we're looking to go in and be very careful with the machining of that. As we get close to the actual specimen shapes, we want our machining to be fairly light and use basically small cuts in the manufacturing process, sharp tools, to try to go in and to end up with a specimen that has minimized work hardening, minimized residual stresses. Also, the final specimen, we want typically for the baseline curve to be polished. What we mean by that, we want the surface to be removed of any machine marks, scratches that would basically be introductions for the cracks. This is one place you do not want to try to cut corners. The specimen manufacturer is probably maybe around $100 a piece, but the quality of these specimens are going to completely drive the quality of the fatigue curve that we create. When we set up the test, one of the first decisions we have to make is the number of specimens. And basically, to get a good baseline curve, you need a minimum of at least 15 specimens. That's going to allow us to accurately determine the curve shape and the scatter within the material. As we increase the number of specimens, we increase the confidence level we have in the data that we are looking at. And we're going to generate a baseline curve that describes the average behavior of the material, but in most cases, you also want to derive a design curve that you can use that will talk about the entire population, a curve that we can design to. And what I mean by that, here I have an example of a strain life curve, and if you look at the plot, the data points, both the blue diamonds as well as the green X's, are actual test data. These are actually specimen tests. The red curve is actually the regression of our strain life curve through that data. And you'll see there that we actually have scatter. Obviously, there is variation from specimen to specimen, even if they were at the same strain level. And that variation, that scatter, allows us to go in and to quantify a certainty of survival for that curve. And so we have the ability to go in and, looking at the scatter, to shift the curve down, or actually we're always looking at a high certainty of survival, so we're always shifting the curve down based on that scatter level. But there's a second issue with this as well. The curve that we're going to look to create is a screen curve. We call that the design curve. And that is not only a factor of the amount of scatter in our test data, but it's also how many tests that we had. The more tests, the more confidence we have in our data, and the stronger that curve can be. In this particular plot, we're looking at a certainty survival of 97%, which basically is 2 standard deviations shift down on the curve. And we're looking at a confidence level of 95%. If I go in and increase the number of tests to calculate this curve, I can go in and improve our design curve. Since we have more confidence, we can actually use a less conservative curve. And so here we see a curve that's at 95% confidence using 10 specimens. If I go to 15 specimens, you'll see that the green curve has moved up. The design curve actually now is closer to the average properties because I have more specimens, I have more confidence in the data. And we have a final plot here that's looking at 25 specimens. Key aspect here, if I'm using this design curve, which typically we will be for our fatigue calculation, going in and trying to get away with a fewer number of specimens to reduce the cost of the test also gives us a design curve that is weaker. Hence, we'll be adding more conservatism to the design. And the cost of that may be far greater than the additional test specimens. Besides the number of specimens, we also have to specify the range of lives that those specimens should cover. And what we need to do is make sure that we have tests that cover the entire range of life of interest for our part. We also, when we develop these strain life curves, we're actually doing separate fits in the low cycle versus the high cycle regime, and we want to ensure that we have enough data points in both regimes, elastic and plastic. Thing we never want to do with these curves, we're fitting this curve through test data, and extrapolation is very unpredictable. You know, the curve has been defined by the test data. Areas outside the test region basically have no control. And so we want to ensure that we're never extrapolating from that curve. We'll see that in just a second. The last couple things to mention, the test data from the high life, high cycle tests cost the most. Those are the ones that run the longest. They're going to have the greatest cost. And so one way of controlling cost on a material test is to identify the high cycle regime that we're interested in, but not go much beyond that if we don't have to. And keeping in note with that, we want to try to avoid runouts. A runout is a test where we shut down the machine without failure, and we've done that after we've hit a predetermined boundary life, you know, maybe 10 million cycles, 20 million cycles, something like that, where we basically say at that point we're no longer interested in the data. One issue with that is that's a very long test. Two, that data point is not used in the determination of the fatigue curve, so it's a wasted data point. So minimizing runouts when we set up the test will give us the most efficient generation of a curve. Here we're looking at just kind of an arbitrary strain life curve, and we're fitting through data. The blue dots here are all data points. This one point out here, with the circle and the arrow, is a designation of a run out. This is a test that we stopped here at looks like about 20 million cycles. So that was actually, that test was terminated, and that data point isn't used in the determination of the strain life curve at all. Now, one thing we want to identify is the valid range of data. What we've got here is a range of lives I feel comfortable with this strain life curve. As I go lower in life or higher in life, that curve is not being defined by the data. It may not be representing the actual behavior of the material at all. So we do not want to go outside that range. The other thing to note here is we are going in and running a test at specific speeds, and we'll see that in just the next slide. But at that test speed, it takes me a certain amount of time to hit the target life that we're running. And one can see here, just as we start looking at the high cycle data, that if I'm sitting out here just under a million cycles, it takes me a day to actually accumulate that test at 10 hertz. And 10 hertz is a reasonable speed for a strain life test. As we go out and try to get close to 10 million cycles, we're looking at a week on the machine. And again, if I were to push that out to higher lives, we keep basically increasing the length of the test. So having bounds on the high cycle regime allows me to go off and make the most efficient test possible. Continuing with specifying the test, one thing that we need to specify is the mean strain that the test will be run at. And almost universally, it'll be at a mean strain of 0, R-1. And the reason for that, in stress life, we may actually run tests at different mean stresses, and that gives us curves that we could use that may be far more accurate than an empirical mean stress correction like Goodman or Gerber. However, in strain life, mean strain and mean stress don't match up. And at the higher load tests, even if I were to run at a different mean strain value, the mean stresses will start to move towards 0. So there's no control of the mean stress by mean strain. So almost invariably, we're going to be running with a 0 mean strain, R-1. With strain life, we're putting fairly large loads into the specimens, especially at the low life regimes. And so we want to pick speeds, test speeds for our test rig that will minimize any sort of part heating. With metallic specimens, we only have to worry about that for the fairly low life regime, but we want to basically control our speeds so we keep a constant temperature on the specimen as we test it. In addition, these test rigs in reality are load control. That's how the test rig actually is activated, but we want to test our specimens under displacement control or strain control. In order to do that, we actually have to measure the strains on this test specimen and put it into a feedback loop to control the load so we always maintain the same strain. That limits the speed that we can run at. So typically on a strain life test, you're running, if we don't have to worry about heating up the specimen, we're running somewhere between 10 and 20 hertz. Now, as we look at very high cycle for strain life tests, there's minimal plasticity, and we can get away with assuming that load and displacement are the same thing. So you'll see a lot of times test labs will go in and at the higher life regime will go in, switch over to load control and allow you to run at a higher speed. So we can at least up the speed of the test for those high cycle regimes and minimize any issues because, again, there's minimal plasticity there. So we can get a higher speeds. One of the key things that you want to understand when you're looking at an SN curve is what the definition of failure is. That curve defines the part failed, but that can mean different things. It could be the fact that I have a load drop-off. So I'm measuring either displacement or load, and as the load drops off during the test, I have a particular percentage, 10%, 20%, that I say the part has failed. Again, that's kind of an indicator of a macro crack in the part. Or it may be pure separation of the specimen. But understanding that gives me an understanding of what the curve actually means. And the last issue here, ideally, we're trying to minimize scatter across the specimens so we can actually quantify the scatter in the material. Ideally, we'd like to have all our tests on a single machine, so we're not looking at variation from machine to machine. And that would be the ideal case in a perfect world. But as you saw, some of those tests, especially the high cycle tests, can run for a substantial amount of time. And if I'm doing those tests sequentially on the same machine, that's going to dictate the duration, how long I have to wait for this test data. So it's allowable to use multiple machines as long as you feel comfortable that the calibration on those machines is kept up to date, so there's minimal scatter due to the different machines. Once we've performed our tests, we now have data, and the data can be in a couple forms. The direct output of the rig, the test rig we've seen, is load, total strain, and life. Load, we're measuring the strain on the specimen, and the part basically has a life that is either the load drop-off or separation of specimens. In addition, typically we are capturing enough data that we're measuring the hysteresis loops as well. So we're able to quantify the hysteresis loops. If I go off and look at just a standard test rig that we have here, what I have on the left-hand side is the actual rig itself, and this upper section is the load cell. That is measuring the load that's transferred to our specimen from the test rig. Our specimen is down here, gripped between these two grips, and attached to it is an extensiometer. Basically, it is a instrument that's clamped onto the specimen at the gauge length, measuring the strains that go on that specimen as I load it. And it actually feeds back to a controller that's controlling the rig. Again, we want to maintain constant strain on this specimen, and we'll see in just a slide that the strain levels are not always tied to load levels. The other two circles here, the first circle is actually, historically, this would have been a control unit, an analog control unit. Today, it's being driven by a computer, and so the display you see here, the CRT, is showing display of what would have been the analog control unit. And this is actually driving the rig, basically maintaining a constant strain, going through looking at the output of the strains from the specimen. And the second display is the data logger. This is actually collecting the data as we run the test. So we're actually tracking load, total strain, but we're also able, in most cases, to go off and track the actual plasticity, the hysteresis loops coming from that. And if you look at the CRT, you can actually see the hysteresis loop that's currently being generated from the test. So with that data, we then can go in and start to generate our strain life curve. And in order to generate the strain life curve, I need to have life. I also need to have elastic and plastic strain. Those are the elements I actually need in my to do the regression for my strain life curve. And I'm going to get that in one of a couple of ways. I could actually synthesize that from load and total strain. If I know load, I know what the stress is in my part because I know the specimen geometry, so I can dictate stress. And if I know stress and Young's modulus, I can get elastic strain that way. Or we could actually go off and get the elastic and plastic strain directly off the hysteresis loops. If we're basically tracking those hysteresis loops, I'm able to go in, plot a loop that's in a cyclically stable point in the test and measure off of it. And we'll see that in just a bit. So I have a couple ways to actually get the data. Ideally, we'd like to measure off the hysteresis loop, and that would eliminate any variation in the Young's modulus. And then what we're going to do with that data is we're going to actually go off and do a linear regression through the elastic and plastic data. So going off and looking at the data coming out of the rig, again, we've had 15 samples. Each sample is run under strain control. And again, you're looking at a close-up here in this picture of that extensiometer measuring the gauge length, measuring the strains. And that feeds back into the test rig, and the test rig is always maintaining that strain. And if we look at a cycle, we'll see that we can go in and track the load and the strain, and using that we can actually predict these hysteresis loops. The load and specimen geometry give me the stress, and so I can start to basically track these hysteresis loops. The reason that we have this fairly complex system is that as we go through and cyclically load these specimens, especially at the low life regime, we're basically developing plasticity. We're yielding the part, and the actual material behavior changes. The first load on the part is following what's called a monotonic stress-strain curve. However, that behavior basically varies as we continue to cycle. And after a few dozen cycles, we will transition to what's called a cyclic stress-strain behavior, or stabilized. And so early on, the stress could be lower or higher than we would expect because we're on the monotonic. And then at the half-life, basically somewhere between the start and end of the middle, between the start and end of the test, we will have stabilized cycles. And in that area, we're going to pull out a hysteresis loop, and that's the loop that we'll actually use to measure elastic and plastic strain. And again, the life is determined by some predetermined either load drop-off or part separation. And so basically from this, we're going to get elastic and plastic strains, and we'll get our life. So now we have elastic, plastic strains, and life. One caveat, we talk about cycles and we also talk about reversals. The actual equation for strain life is in reversals, and there's 2 reversals per cycle. A reversal is just a change in direction of the loading. And so we're typically interested in cycles, but the equation itself is driven by 2NF, which means basically reversals. And here we see a series of test data. Those red dots are the total strain that were measured for different strain levels, and each one is plotted strain amplitude versus life and reversals. And if we look at the equations up here, the equation for the strain life curve is this bottom equation, and it's comprised, the first component here is actually the elastic portion of the strain. So this is looking at elastic strains, and it generates what would be a high cycle behavior. The second term here is looking at the plastic strains, and it's basically driving the low cycle behavior. We don't actually fit this curve through these data points. What we do actually is take the total strains and we use either the load stress information, or we measure directly off the hysteresis loop, but we basically dissect the total strain first into elastic strains. So now these are the elastic strains, the elastic portion of the strain from the total. And from these elastic strains, we basically do a linear regression. Again, this is on a log-log plot, and so we end up basically regressing this, what we call the elastic line or strength line, through the elastic data. And from this, we get two parameters for the strain life equation. One is B, which is the slope of this elastic line, and the other is the intercept. The intercept is described in stress because it's elastic. We're just dividing it by E, so it goes on the strain axis, which is the vertical axis. So the sigma F prime and B are the parameters for the high cycle behavior. In addition, we take and we also extract the plastic strains from the total, and we regress a second line through that. So that green line there is the plastic line, or the ductility curve. And again, it provides two more pieces of data. C here is the slope of that, and epsilon F prime is the intercept. And those four pieces of data, B and C as the slopes, and sigma F prime and epsilon F prime, basically are the components, the parameters I need to describe the strain life curve. So the strain life curve actually is the addition of those two straight curves in log-log space. So we're going to actually do our calculation with this red curve. The total, basically, this is the actual strain life curve, but it is actually computed from separate regressions to elastic and plastic strains. Because we're interested in plasticity, we need to have stress-strain behavior as well. Many times, especially for moderately low to high cycle behavior, plasticity is done inside of the fatigue program, which means we have to have the stress-strain curve there to do our fatigue calculations. If we're at very low lives, we need to do the plasticity in the fine element program, but we still need to have stress-strain behavior there as well. So we need to get the stress-strain curve defined, and there's two ways to do it. We could calculate it directly off of the hysteresis loops that are being collected as we do the test. And again, we take that hysteresis loop from half-life, basically somewhere in the middle of the test, so we have stabilized behavior. Or it can actually be done in separate tests. So we could either utilize the fatigue tests data to do the regression, or we can go off and do separate tests. In our lab, we tend to use the fatigue tests. However, I have had customers that feel that they can go off and have more flexibility in running separate tests to get the stress-strain behavior. If we're going in and using the fatigue test to generate this curve, what we're actually going to do is we're going to have a whole family of hysteresis curves, each one of these at a different strain level. And so at the lower strains, there's smaller hysteresis curves, and as we have higher strains, they become larger. And what we do is we pick the upper corner of the hysteresis curve, and that point is used as a stress-strain value on my stress-strain curve. So what you're looking at here, these blue dots, are basically this upper vertex of the hysteresis loop for different load levels. And what we're going to do is regress a curve through that. The stress-strain behavior that we use for fatigue is written as a Ramberg-Osgood equation, which is nothing more than saying that the strain is elastic part and plastic. And this plastic piece right here is nothing more than a straight line curve in log-log space of plastic strain and stress. So we basically are going to take these points, go in, plot the plastic portion of the strains on log-log curve, and just fit a straight line through this. And n is the slope of the curve, and k prime, n prime is the slope of the curve, and k prime is the intercept at a strain of 1. So with the stress-strain behavior, the cyclically stable stress-strain behavior, stress-strain curve, and the strain life curve, we now have enough data to go off and do a crack initiation fatigue analysis. So in summary, walk through the steps we've talked about, the things that we had to kind of at least answer questions to the test lab that or to our internal test lab for a company, things that we need to worry about. again, the test specimens. And again, we want the specimens to be made of material that as closely as possible represents the material of our part. Composition, microstructure, heat treat. The preparation of the specimens is critical. We want to guarantee that when we end up with a specimen that it's dimensionally correct, so there's no variation across, minimal variation across specimens, as well as it's a geometry that as I apply a tension load, I'm not inducing things like bending because of misalignment of the specimen. I want to control the final surface finish on the specimen. And when we say polished, it's not like a mirror where I see myself in the specimen, but we want to eliminate any machine marks, scratches that would be initiation points for that. In terms of number of tests, we want a minimum of 15 tests to do a baseline curve. And actually 20 to 25 would be better. Again, the more specimens, the higher the confidence level, the less conservative the design curve has to be. You want to guarantee that you have tests throughout the range of lives that we have to look at for our component. So we never want to extrapolate outside the range of data we have. And again, we want to make sure that we have sufficient tests, that we have data points that we can go off and look at the high cycle behavior and the low cycle behavior. Because again, we're going to fit lines through both those regimes. One thing, if you're having this test done on the outside at a lab, you want to require that you get access to the raw data. For each test, you want as much data as they've computed. At the minimum, that would be, again, stress, total strain, and life. But in most cases, they will have captured the hysteresis behavior and have measured values for elastic and plastic strain as well. And you want that data. Again, you need to understand the range of the data to know where you can actually use this curve and you can't. Again, strains obtained directly from the hysteresis loop are preferable. That's going back to the thing. And then finally, in terms of data fitting, the actual fitting of this data is more complex than just doing an Excel trend line. We're actually controlling the strains on the test, and the lives are the outcome. And but basically the lives are the x-axis, the strains are the y-axis of our curve. On a simple regression using like a trend line inside of Excel, it reverses the independent and dependent variables. The independent variable being the y-axis in our test, where typically on just a standard regression it's the x. And so the data manipulation regression is a little more complex than just going off and just doing a simple Excel calculation using trendline. Okay, with that, I guess we can open up to questions.